Coming up on part 2 of this special 2-part Destination Tomorrow, we take a look at food technology and how it is used by NASA. We'll see what the future holds for food technology on long-duration missions to planets like Mars. Plus, Johnny Alonso speaks with astronaut Mike Foale to find out what it is like to live and eat in space. All this and more next on Destination Tomorrow. Hello everyone, I'm Kara O'Brien and welcome to part 2 of this special edition of Destination Tomorrow. In part 1, we found out how NASA researchers have made improvements in the types of foods astronauts have eaten since the beginning of the space program up till today. On this program, we will be discussing future food technologies and how they'll be used on long-duration missions. Recently, it was announced that NASA is planning to send a crewed mission back to the Moon and to Mars. Obviously, huge technological challenges will need to be overcome before these missions can be successfully accomplished. NASA researchers realize that trips like these will require building the appropriate type of spacecraft, having flawless life support systems, and will need the right tools to perform work once we arrive on these distant worlds. But a major concern that often gets overlooked by the general public is what types of food will be eaten by our astronauts on these long missions. Fortunately, previous missions to low Earth orbit in the Space Shuttle and longer missions aboard the International Space Station have helped NASA better understand how food and the astronaut interact, but not much is known about how food will fare on these long missions. The primary goal of the food systems in these long missions will be to provide a palatable, nutritious, and safe food for our explorers, while also taking up as little room as possible. Food is vital for survival here on Earth, but is even more important in some respects in space. Its preparation, quantity, and quality are critical and can affect astronauts on a physiological level. One of the most crucial problems on long missions is bone loss. Typically, astronauts lose 1 to 2% of bone mass each month that they are in space, especially in the lower halves of their bodies. In the weightless environment of space, there is almost no stress on the skeletal system. Bones are no longer providing support to walk and are not being used to maintain body posture. This lack of stress on the bones may be a key factor in an astronaut's progressive bone loss in space. Other problems like fluid shift and space motion sickness must be taken into account when providing food to the astronaut crews. Meals must be chosen that can help slow many of the problems faced by astronauts. Another major concern for NASA food scientists is the stability of food that is packaged for these missions. It's vital that the food remain edible for years at a time, staying safe and stable aboard the spacecraft. This is perhaps one of the most important factors of the planned long-duration missions. If the food spoils, there are no options currently available to astronauts for nourishment. With missions to Mars requiring at least 3 years to complete, stored food must remain shelf-stable for that time, preferably longer. In the short term, food systems that are currently being used aboard the shuttle and space station are suitable for transit to another world. But once astronauts arrive, other alternatives need to be considered. With these thoughts in mind, researchers at NASA are developing new ways to help crews eat well in space. In addition to storing food aboard the spacecraft, many at NASA believe that growing food in space or on planetary surfaces will need to be perfected to help feed astronauts on these long missions. Coming up, Jennifer Pulley speaks with Dr. Michelle Perchonik at NASA Johnson Space Center to find out about foods of the future. But first, did you know that freeze-dried ice cream sold in many museums today is not really eaten by our astronauts in space? In the mid-1960s, scientists blended and froze a mixture of coconut fat, milk solids, and sugar, then ground and compressed the mixture into cubes under high pressure, making a freeze-dried ice cream. This concoction was only taken into space once. In 1968, the Apollo 7 astronauts tested it while orbiting Earth. Although it is not known exactly what the crew thought of the ice cream, it's telling it was put on only one mission. Incidentally, the product sold today in the museum is produced differently. It is simply ice cream cut into cubes, then freeze-dried.
One of the biggest challenges facing NASA in the development of long-duration space missions is food. In centuries past, explorers could almost always find food in their surroundings, even if they were thousands of miles from home. Of course, this same luxury will not be afforded to space travelers. They will have to rely solely on food that is taken with them, or that can be grown during the mission in the vehicle or on the planetary surface. Although this may seem daunting, researchers at NASA are now developing viable systems to help keep our astronauts well fed on long space missions. I spoke with National Space Biomedical Research Institute food scientist, Dr. Michelle Perchanik, here at NASA Johnson Space Center to find out more.
Well, we have several goals. First is safety. We have to make sure the food is safe so that the crew doesn't get sick. Second of all, we have to make sure it's nutritious. The crew is getting all of their nutrition from the food. And thirdly is acceptability. If the food isn't acceptable, the crew is not going to like it. And we know that as the duration of the missions get longer, we need to make sure that that food is acceptable to them. And we do testing, and we'll be doing testing here at Johnson Space Center on the acceptability of the food with the general Johnson Space Center public, and then later with the actual crews.
So what are some of the challenges that you'll have to overcome?
Well, first of all, it's going to take us 6 to 8 months to get to Mars with the current propulsion system. And yes, there are engineers here at NASA trying to get the propulsion systems improved, but right now it's 6 to 8 months. And of course, 6 to 8 months home. And because of the way the planets align with each other, it's going to be 18 months on the surface. So the mission is going to be somewhere on the order of 2.5 to 3 years long. So what that means is we're going to have two kinds of food systems. The first is a transit food system. On the vehicle, because of microgravity, it is very difficult or almost impossible to do any sort of preparation or cooking of the food. So we're going to have a food system that's very similar to the ISS food system, prepackaged foods. Most likely they'll be stored at room temperature, so we won't have a refrigerator or a freezer. Well, that gives us some challenges because it's very difficult to find some foods that have a 3 to 5 year shelf life at room temperature and that you're not keeping it frozen or even at refrigerated temperatures. The other part of the challenge is looking at the packaging materials to make sure that we have the barrier properties to provide us with that 3 to 5 year challenge. So we have that issue. Now, think about it, 6 months, you've got all these packages of food because at each meal, you've got about 3 to 5 packages of food for each crew member times 3 meals and snacks. How do you store all this? Not only are you storing it at ambient or room temperatures, but you have to keep track of it, inventory management and tracking and knowing where it is and how much you've used and when you've used it. So the challenges are unbelievable, even just for the transit mission.
Right.
And even though we've done it already on ISS and shuttle, we've got that many more challenges to go after for this.
One of the main challenges for NASA planners will be to provide food that will help keep crews healthy and happy, while also helping the astronauts' bodies acclimate to the rigors of space travel. During these long missions, astronaut physiology will need to be taken into consideration. The human body has adapted to the effects of gravity here on Earth. But once gravity is reduced, the body slowly begins to adapt to its new surroundings. During this adaptation process, weight loss, dehydration, constipation, electrolyte imbalance, bone loss, and a myriad of other problems may occur. To help prevent or alleviate many of these problems, researchers are investigating the levels of nutrients each astronaut may need. Proper diet and exercise should counteract many of the problems associated with the physiological changes. So that takes care of the transit, of getting to Mars. Once they're there, on Mars, then what?
Well, then we have the opportunity to use the gravity of Mars. Mars has 1/3 gravity. So that's a little bit of gravity, enough to keep things down towards our feet. And with that, we can start looking at processing and preparing food. Now, we may be growing some of these crops, or we may be bringing up these items in bulk, such as soybeans or wheat. We will have to grow the vegetables and fruits because those don't have the shelf life we need. When I talk about bulk, what we're saying is we're going to bring up in large quantities unprocessed foods that you would then add in either through processing or maybe in the recipe. So for example, we would bring up large quantities of soybeans, and then we could use those soybeans to process into texturized vegetable proteins, or maybe we make it into tofu. So we would have that opportunity for more variety, therefore more acceptability in the processed food system. We'll also be bringing up items that will help us do the preparation in the galley, such as dried herbs and spices, or dried non-fat dry milk, or maybe dried egg whites, because it's going to be hard to bake a cookie or a cake without those kinds of ingredients, in addition to the baking soda and baking powder. So we're looking at all those different ingredients, what the quantities might be, and whether they will also last that 3 to 5 year shelf life, and how we're going to store them. We think we'll have to store the soybeans and the wheat berries at refrigerated temperatures and probably in a non-oxygen atmosphere. Oxygen's not food's friend, and we want to keep the oxygen away from those bulk ingredients until they're used.
Other than providing bulk foods, there is also a plan for astronauts to grow food once they arrive and set up planetary bases. The plan would consist of crews growing crops hydroponically, which means to grow the food by using water rather than soil. Having fresh crops would not only provide variety in the menu, but would also offer great psychological benefits to the crews as well. With both fresh foods and bulk ingredients, crews would be able to process many of the foods that they would be eating. Processing food would consist of taking one type of food and making it into many different types of foods. As Michelle mentioned, foods such as soybeans could be processed and made into tofu, soy milk, soy oil, soy flour, and many other items. Other foods that would be ideal for processing include potatoes, wheat, rice, tomatoes, and peanuts. With the right equipment, crews could potentially grow and process large amounts of the food they would need to survive on site, rather than solely relying on food from Earth.
Well, processing is not so hard down here, but now we need to worry about not bringing up too much weight, too much volume, and trying to be multifunctional with the equipment. For example, maybe a piece of equipment will not only make pasta, but it'll also mill wheat berries, and it may also make cereal for breakfast. Crew time is an issue. You don't want the crew to be spending all their time processing and preparing the foods, because they want to be out there exploring and doing real science.
Weight is going to be a major factor in getting crews to other planets. Knowing this, NASA planners are deciding if they should provide multifunctional processing equipment or if they should rely on age-old proven methods of food processing.
For example, how do we make bread? Well, we could do the more modern way of putting everything into the bread maker and letting it happen, or we could actually just go the old-fashioned way, mix all the dough up, knead it, let it rise, knead it again, let it rise again, and then bake it. And we're going to have to be looking at where that fine line is on crew time versus automation and the mass that we would have to uplift to the Mars surface. They're not at Mars to do cooking. You know, they can do that at home. They're there to explore.
To help make NASA's exploration goals a reality, NASA planners are also relying on outside help. Many colleges, universities, and other entities are performing experiments on food and processing equipment that may someday be used in the space program. The expertise that is being provided will help focus and quicken the development of technologies that will make exploration possible.
We are a small group here, and we're not the experts in everything, so we go externally. For example, we have a researcher at UC Davis looking at developing, and he's actually built a prototype on a multi-purpose fruit and vegetable processor, testing it using tomatoes, but again, a multi-purpose piece of equipment that will dice, cut, concentrate the tomatoes or anything else. One of our faculty fellows actually has looked at radiation issues. We know that radiation is going to be an issue. We know it for the crew as well as, we believe, for the food, but we don't know at what extent. So Dr. Wilson's been working on how radiation affects soybean functionality, and he's looking at it on two sides. Again, the safety side. If you're going to bring up bulk ingredients, you need to make sure they're clean and safe before you bring them up. Then he also is looking at what kind of radiation they may incur during a mission to Mars. We don't have the atmosphere here on Earth on Mars, so he's looking at how that's affecting, for him, the tofu processing or manufacture. And he's finding that, yes, at higher levels of radiation, the tofu isn't made quite as firm, and it has an off flavor and aroma to it because we get that rancidity from the oil.
Well, Michelle, it seems like you